Can you see that? Is it full screen now?
Yes, it's great.
Okay, so thank you to the Maxwell Society for organizing this. So I'm not feeling very well today. I don't know what's wrong with me, but I've given them instructions to call an ambulance in case I collapse. I've got a thing about trying to power through talks whenever possible. So my first postdoc was in Brussels, and I was doing my PhD in Sussex, in Brighton. I chose Sussex because it had the most sunshine hours of any campus in the UK. And I went to Brussels and I had full-blown flu, and I went to my supervisor before I went. I said, should I go? And he said, just go, you've got to go. So I went, and it was hell. It was awful, and I was sweating and feverish. But anyway, and it turned out that in Brussels, they had visitors from the Moscow Institute of Nuclear Research. And if you know the archetypal Russian scientist, they slammed me. I was giving a talk about 5-dimensional supergravity, and they killed me, and they were merciless. And I survived. At the end of it, I had to have a lie down. But then one of those people from Russia is still a friend of mine. My wife knows his wife. I know his children. We've written papers together, very highly cited papers. So I make it a point of always trying to turn up to a talk whenever possible. So here I am. And I'm going to be talking about, can you see, has the slide changed?
Yes, it has. It's
very good. Okay, so everything's good then. So I'll be talking about what can we do with dark matter detectors other than looking for dark matter. In particular, new interactions between neutrinos and other particles and CNO neutrinos. Okay, so I'll explain what all these things mean, hopefully. So here is an old picture of the Milky Way based on a paper that I wrote a long time ago. So it's a bit old, but basically it's the really good illustration of what a galaxy looks like. You've got the stars in white and you've got the gas in blue, and it looks like a spiral galaxy. But the bit that you can't see, that we believe is in every single galaxy, is a big halo of dark matter. Now, dark matter is obviously green, as you'll see now. And you see the dark matter is much, much bigger than the baryonic center. The bit of the galaxy that you can see is just a tiny little jewel embedded in the center of this big dark matter halo. And we don't know what this dark matter is, okay? So also, this is a scale image of Andromeda galaxy, which is the nearest big galaxy to us. It's versus the moon in terms of angular size. So you can see Andromeda is huge on the sky. But the big circle around Andromeda is the dark matter of Andromeda. It would be even huger. The reason why you can't see Andromeda itself is because it's quite faint, it's a long way away, so you can only see the center of it on a good night, unless you've got a big telescope. The reason why you can't see the dark matter is because you can't bounce photons off it. And the way that I can see you is by photons bouncing off your face and coming to my eyes. Of course, it's a bit more complicated when we're on Zoom, but let's not go down that route. Okay, and there's 6 times as much dark matter as normal matter, okay? And we don't know what it is. We know that we can't see it. It doesn't interact with itself. So if dark matter is a particle, what kind of particle is it? It's certainly invisible. We can't see it. Now maybe, and there's good reason to believe that this might be possible, maybe there's an interaction between dark matter and normal matter. So in particle physics, everything's a particle. Matter itself is made out of particles, and the force between particles is mediated by particles. So it might be that dark matter interacts with normal matter by exchanging a messenger particle, which might mediate a force between dark matter and normal matter. Now, we've been looking for this interaction, and what we know so far is that it's very, very weak. Okay, if it's there at all, it's very, very weak, but we keep on trying to search for it. And we're quite agnostic about what it could be. So we just say on the left, you've got dark matter particles coming in to collide and disappear to form 2 standard model particles coming out on the right-hand side. And you can just write it as a gray blob if you want and still try and figure out if it's there or not, if there's any kind of interaction. And there's all sorts of level of complexity. Some people have got very detailed models as to what the dark matter is. Some people are completely agnostic and just try and see if they can create any dark matter at all, okay? Now, there are 3 classical ways to detect dark matter. You can make it, so at the LHC is a reverse nuclear reactor. You speed up protons using magnetic fields, and you give them a huge kinetic energy, and you smash them together, and you hope that you can create some dark matter particles. So It's converting energy, kinetic energy, into matter, as opposed to a nuclear reactor, which converts matter into energy. So it's E equals mc squared backwards. Now, the complicated thing is if you do produce dark matter at the LHC, it's going to fly out of the detector without making the detector go bing. The detector's not going to see it. So what you have to do is you have to look for missing energy. So we all know that energy and momentum are conserved. So you have to make sure that you follow the energy and momentum of all the particles in the collision. And if you see somewhere where it's not conserved and there's some energy flying off in one direction, it might be a neutrino, it might be dark matter. So you need to find out about the 4 vector so you can get the P0 component of the 4 vector, which of course is the mass, right? The other way that you can look for dark matter is you can break it. So you look into regions of the sky where there's lots and lots of dark matter, and you wait for if the dark matter interacts with standard model particles, the dark matter should also annihilate with itself and create standard model particles. So you look for high energy particles like gamma rays or neutrinos that are produced by the annihilation of dark matter with itself. The third way, so someone's raised their hands. What's the deal with questions? Are we doing them as we go along? Because I'm fine. The chairman has to decide.
So I think what we should do is we should just have people write stuff in the Q&A. And then you can answer questions either throughout or at the end, whatever you feel most comfortable with.
So I can't read the Q&A. If you want me to answer questions throughout, you're going to have to give them to me verbally, okay? Because I can't read. Experience has taught me I can't read the chat and give the presentation. Okay?
Wonderful. Then I think we should save them all for the end. That's what we've been doing for other talks.
That's fine by me. Either's fine by me. If there's an urgent one, feel free to shout out. Okay. So the other thing you can do is you can smash dark matter particles together and they'll produce either gamma rays or neutrinos or high energy particles, and you can look for them. Today, we're going to be talking about shaking dark matter. So we're going to be waiting for the dark matter to come in from space, bounce off a particle, a normal particle here on Earth, and then impart some energy to it. Of course, we can't just have any particle. We need that particle to be inside a detector. And it has to be a very sensitive detector. Because while we know how much dark matter there is in this region of the universe, in this region of the Milky Way, it's 0.3 protons worth in every centimeter cubed. And while we know how quickly it's moving about 200 or 300 kilometers per second, we don't know if there's lots of big particles or, sorry, lots of tiny particles or just a few big particles. And we don't know what the cross section is for them to interact with us. So we don't know what the probability of them interacting with us is. This is, at the moment, the most sensitive dark matter detector on the planet. It's called XENON 1 ton. It's located in Italy, but it's not just Italian. It's a huge international collaboration. It's underneath the hills, which are north of Rome. So if you've ever had wine called Montepulciano d'Abruzzo, the Montepulciano has got a dark matter detector inside it. And it's made of liquid xenon. Xenon is very, very dense. And of course, it's and when dark matter particles, if dark matter particles interact with the xenon, they'll create a little bit of, they'll knock an electron off, and they'll also they'll produce some photons. And it's looking for both the electrons and the photons. And it hasn't seen anything. All it's got is this constraint on the cross section. So this kind of dark matter, we sometimes call it WIMPs. These dark matter particles, the cross section for it to interact with the nucleon, all we know is that it's, depending on the mass, it's below this yellow and green line, okay? Now, for a high mass, we don't have such a good constraint, okay? Because the reason is, if it's a very high mass, there's not many dark matter particles. And so as we go to higher masses, it becomes weaker. Now, for low mass, we don't have a very good constraint because as you go to lower masses, the kinetic energy of each individual particle, because the velocity is the same, whether it's high mass or low mass, the kinetic energy is not enough to make the detector go bing, so you can't detect it. So you lose sensitivity at both high mass and low mass for different energies. And the best sensitivity it has is about 30 GeV. And this is about 10 to the 20 times less than the typical interaction between two neutrons. So it's tiny, tiny cross-section, right? Now, at the moment, there's an upgrade of xenon, which is 6 tons instead of 1 ton. And there's also an experiment that the British are involved in, called Lux Zeppelin, which is in it's in North America. I think it's in a gold mine in South Dakota, and this one is it's about the same mass. It's also liquid xenon, and they're both going to switch on soon. They're racing each other to see who gets the results soon. I think they might be operating now, but they're very secretive. but no dark matter has been detected. We know how much dark matter is around us and how fast it's moving. Why can't we see it? Well, maybe the dark matter is too light. I told you that we lost sensitivity if the dark matter is too light because each dark matter particle doesn't have the kinetic energy to make the detector go bing. So that might be one explanation. It might just be that the dark matter doesn't really want to talk to normal particles at all. Standard model particles, the stuff that we're made out of and the stuff that the detector's made out of. But what's happened recently, and something I've become interested in, is that we better start to detect the dark matter soon, because if we don't, we're going to have a problem, and that's we're going to start seeing neutrinos. The dark matter detectors are becoming so sensitive that they're actually going to detect neutrinos in a way that neutrinos have never been detected before. Now, the neutrinos on the Earth, there are three different kinds of neutrinos. The first is the neutrinos that come from the nuclear reactions in the sun. And this is the PP cycle, which dominates the conversion of hydrogen into helium in the sun. And whenever you see a mu here, one of these nuclear reactions creates a neutrino. There's also cosmic rays hitting the atmosphere, and they create big showers, like big crash. It's like if you take an electron and bounce it off something, it's like playing snooker. But if you take a proton and bounce it off something, it's like hitting someone in the face with a custard pie. And it all goes all over the place, all right? And so all these bits fly off and hadronize, and you get pions of the nucleons, muons, electrons, and loads of neutrinos. So these are higher energy than these neutrinos. And finally, in 1987, we observed a supernova, which wasn't even in the galaxy. We're well overdue a supernova. A lot of particle phenomenologists are very angry at the universe right now because we are well overdue a supernova in the Milky Way. The nearest one that we've seen while we had decent detectors was in 1987, which was a good year for music, if you look at Top of the Pops. But it wasn't a brilliant year for neutrino detectors but they had started building them. This is the aftermath of supernova 1987A. These are the precious neutrinos that were detected after that supernova. And you see Kamiokande, which has been replaced by Super Kamiokande, which will soon be replaced by Hyper Kamiokande in Japan. IMB in the States and Baksan in Russia, they all detected a handful of neutrinos. These are the neutrinos that they detected, extremely precious. And these neutrinos are extremely precious data that people have used since 1987 to put constraints on all sorts of things, because you have access to a thermal environment which is about 100 MeV. And that's hotter than we can see when we look back into the Big Bang. Okay, so this is super, super important to get another supernova going off. Now, you imagine it's not just supernovae in the Milky Way that go off. There are supernovae that go off throughout the universe. All galaxies have got big stars that go supernova and create neutrinos. And you integrate all of the neutrinos that have occurred from all the supernovae that have occurred throughout the history of the universe, and you have this diffuse supernova neutrino background. So those are the three sources of neutrinos that we get at the Earth. Apart, there's some geoneutrinos at all. I'm not going to talk about them today. They're from nuclear reactions inside the Earth. Now, solar neutrinos, we're mainly going to talk about them today. They give rise, the amount of recoil energy that they give, it depends what they hit, right? And it depends which one they are, because the solar neutrinos, some of them have got like 10 to the minus 1 MeV or 0.3 MeV, and some of them have got like more than 10 MeV. So it's like 2 orders of magnitude of energy. So some of them, they can hit electrons, which is the way that people normally look for neutrinos. And if they do hit electrons, they can lead to KeV recoils or MeV recoils. You should be able to do the recoil just using 4 vectors and conservation of energy and momentum, if you've got that far in your course. If you haven't, you will. But they can also scatter off protons and nucleons inside the core of the atom. And that's a nuclear recoil. And that only produces low energy recoils, KeV recoils, which haven't been seen before. In fact, the first time anybody saw the interaction of neutrinos with nuclei as opposed to electrons was really recently, about 2 years ago. And what they discovered was that they do interact with nuclei, but because they're low energy and they've got a big Compton wavelength, they don't just interact with one nucleon or one proton or one neutron. They kind of interact with the whole atom coherently, which is really weird. It's good for us because it makes the cross-section bigger. But the recoil you get is very low energy. So you need a very, very sensitive detector, because you need a detector with a very low energy threshold so that you can get a recoil that you can observe. So what they obsess with is getting big detector as possible with the lowest possible energy threshold. And with that, they can look for more kinds of dark matter and more kinds of neutrinos, and that's the game. Now, what that means, if we're going to start seeing neutrinos at dark matter detectors, is you might not see the dark matter because of all the neutrinos. And there's this famous plot here, which is called the neutrino problem. And if you get your cross-section that you're sensitive to down far enough by building bigger and bigger and bigger detectors that are more and more sensitive, you get to a point at which you start to see neutrinos due to cosmic rays in the atmosphere and diffuse supernova. And then over here, you start to see the solar neutrinos coming from the sun at lower energies. They give rise to lower, and they look like different kinds of dark matter. So this is a problem. And I've done some work on how to get around this problem. But you can also embrace this, and you can say, well, hold on a minute. We've got these dark matter detectors, and they might not detect any dark matter at all. But they can detect the neutrinos from the sun, and they can do it in a different way to any of the detectors that we've got today, because all of the detectors we've got today use the interaction of neutrinos with electrons. But the dark matter detectors, you might be sensitive to the interaction of neutrinos with nuclei, with neutrons and protons. And that means you can look for exotic new physics. Because you're probing the cross-section in a different energy range, there might be some new physics down there, like a new interaction particle that you didn't know existed. And so some of the work that I've done is trying to understand, if there was a new particle, what the rates of neutrinos that you would observe at different detectors that are coming online in the next year or so, how those rates would change depending on different kinds of new physics. So different kinds of new forces between neutrinos and nucleons that correspond to both interactions between neutrinos and nucleons, but also neutrinos and electrons, new mediators, new particles, new forces. Now, interestingly, last June, during lockdown, the XENON 1 ton experiment looked at the electron recoils that it was getting, and it tried to fit them all because they've got a huge background. There's lots and lots of radioactive stuff that also creates signals, and they have to really understand all that radioactive stuff and then take that away from their total rate. And they observed, when they did their best bet of all their stuff, they got this red line, but what they actually observed was these black data points. And they claimed that this was kind of statistically significant evidence of having an excess of events. So it was almost like there was a new interaction between neutrinos and electrons that wasn't the standard model. So it wasn't due to W or Z bosons. It was something beyond the standard model, some crazy new physics. And there was a whole load of papers. I wrote a paper as well because I had to, because everybody else, we'd written a paper a few years ago and I didn't want everybody else to clean up on the attention. So I feel a bit guilty about that. If you write a paper really quickly, people call it ambulance chasing. And that's okay. Sometimes I do that. More often I don't. And we came to the conclusion that you could explain this excess as it being due to solar neutrinos from the sun, interacting with electrons, but with a new force, not a standard model force, a new mediator with a very, very small mass, sort of tens of keV, as opposed to sort of 90 or 80 GeV, which is the mass of the W and Z bosons. So a new interaction that only occurs at low energy. So we said that, but in the same paper, we said, that's good, but if that's true, we've got some problems. The reason we've got some problems is because of the evolution of stars, okay? So if you look at a red giant star, what happens is that the core turns into hydrogen burns into helium. When it runs out, you get a helium core which grows, and on the surface, you get more hydrogen burning into helium, and the outer bit blows out. But then at some point, the core gets so dense and so hot that helium burning takes place. Now, if you've got new interactions that are not standard model interactions, then those extra forces, they can cool down the plasma. Those extra bosons, they can remove energy from the plasma, and you have to include them in the equations of stellar structure. And they would delay the moment at which the helium core started to burn. Okay, so the red giant would be bigger, 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 and the helium is not going to kick in because this new interaction had cooled down the stuff in the middle more than the standard model would. And here's a picture of the globular cluster that I took with some undergraduate students from the roof of the King's building. that unfortunately we're not allowed to go to at the moment. And this is a lovely globular cluster. It's got some old stars in it. And if you look at the Hertzsprung-Russell diagram, so this is the magnitude. So for historical reasons, the Hertzsprung-Russell diagram is logarithmic and backwards. So as you go up, you've got higher luminosity, so it's a brighter star. But as you go to the right, you've got cooler stars. Now up here is where you get the red giants, and they go up and up and up here, and they get growing luminosity until they start helium burning, and then they go down to this horizontal branch over here, okay? And if you see how far this tip goes up, you can tell if there are new physics that are cooling down stars, because if there's something cooling down the stars, it'll get even higher before it starts burning helium. So by analyzing stars, people think that the interpretation of the excess that we saw is impossible. And we wrote about that in our paper too. So all these things are connected. So this is the beautiful thing about astroparticle physics, is you can bring together lots and lots of different things. Now, what I'm going to talk about in the rest of the talk is something else that you might be able to do with dark matter detectors, and that's looking for CNO neutrinos. So this is a front cover of New Scientist from less than 3 years ago, and it says something strange is going on inside the sun. Is it? No, it's less than 4 years ago. It's October 2017. Now, what are they talking about? Now, what are stars? Stars are solutions of the stellar equations of evolution. So you have conservation of mass, you have hydrostatic equilibrium, gravitational force down equals pressure gradient up. You've got the luminosity passing through the star, and you've also got the temperature gradient. And by solving these equations on a computer, you end up with different stars. And this line here corresponds to the main sequence of stars. So these are stars that are just burning hydrogen into helium. And they've got a particular luminosity for each temperature. And you can see there's a kink here. And that's because these stars down here that are low luminosity and low temperature, they are burning hydrogen into helium via the proton-proton nuclear reactions. But these stars up here, they are higher temperature, and they use a different mechanism to convert hydrogen to helium. They use the CNO cycle. So this is the PP chain on the left that produces helium. The CNO cycle is a bit more complicated. It kind of uses carbon, nitrogen, and oxygen as a catalyst to do the burning, okay? But both of them produce neutrinos, and you can look for both neutrino signals. Now, the reason why there's much more PP than CNO in the sun is because it's relatively low temperature, and CNO is much more temperature dependent. So down here, at the core temperature is what it is for the sun, the PP dominates. So there's a problem here, and we don't really understand the sun, which we should try and understand because it's very close to us, and it's the basis for our knowledge about the entire universe. And the problem is, if you look at the sun using a very, very high precision spectroscope, you see all these absorption lines, and they correspond to all the different elements which exist in the sun. And as the photons pass out of the sun, they get absorbed at particular wavelengths, and it tells you precisely what the spectral abundance is of the sun, the solar spectral abundance. And people get one particular value. And of course, the interesting thing is that inside the sun, you say, what you do if you're an astrophysicist is you say that X is the fraction by mass of hydrogen, Y is the fraction by mass of helium, and Z is the fraction by mass of everything else. And actually that's dominated by carbon, nitrogen, and oxygen. But because the CNO cycle is dominated by, is catalyzed by carbon, nitrogen, and oxygen, it doesn't only depend on temperature, it also depends on Z, okay? So if you are able to look at the surface of the sun and work out all the elements that are there, in principle, you can figure out how much carbon, nitrogen, and oxygen there is in the sun. And then you can figure out how much CNO burning there should be. But there's another way of studying the sun, and that's seismology. This is seismology of the Earth, which you're probably familiar with. If you get an earthquake, it sends a sound wave through the Earth, and then you get discontinuities at different layers, just as you do, you know, because the speed of sound changes. And what's happening is you're measuring the speed of sound as a function of depth, depending on where you send it and where you pick it up. And from that, you can find out about the internal composition of the Earth. You can do the same with the sun. This is called helioseismology. and the sun ripples, and it's got waves that are passing around inside it. And the smaller waves, they don't go very deep, but the lower waves, they go very, very deep inside. If you split this into spherical harmonics, then the L equals 0 is a very long wavelength, and L equals 75 is a short wavelength. So by looking at these different ripples and decomposing this and doing like a Fourier transform and using a very sensitive spectroscope to watch these ripples, you can find out what the speed of sound is as a function of depth. And the problem is that the speed of sound as a function of depth in the sun is observed by helioseismology. It's not the same as the speed of sound as a function of depth in the sun that is predicted by looking at the solar spectral abundance, by looking at the spectral lines on the surface. So we don't know what's going on. It's probably because if you've got the pressure and the density as a function of depth, you've got the speed of sound. So if you measure the speed of sound as a function of depth, you know what's going on here. You can come up with a model that corresponds to the solar spectral abundance on the surface, and you can see that you get the wrong speed of sound in the middle. There's a discrepancy between the two methods. Okay, so if they agreed, then these curved lines would match up with the dotted line, and they don't. Now, this could be due to just us modeling the sun wrong, and it probably is, but it could also be due to crazy stuff going on, which is what I always hope as a particle phenomenologist. It could be due to new particles that don't interact very much with the plasma at all. So you give them a kick in one region of the sun, and they go for a long distance, and then they dump their energy back into the sun somewhere else. Now, if you do that, you have the effect of changing the opacity of the sun. It changes the way the energy flows through the sun, which changes the temperature gradient, which changes the density, which changes the speed of sound as a function of depth. So I think we really need to try and understand the sun in a lot more detail. So we want to get another way of finding out how much carbon, nitrogen, oxygen there is in the sun. But of course, we can look for the neutrinos, but it's very, very difficult, right? So if I look at the CNO neutrinos, we've got the fluorine, don't worry about that, and the nitrogen and the oxygen, okay? There's the dark blue one here, and the green one there, and the cyan one there. So the fluorine's no good at all. So here at higher energies, you've got these boron-8 neutrinos, and then you've got this huge spike due to these PEP neutrinos. So below this spike completely dominates everything, because once you take into account the spreading of the energy, because you get different scattering angles, you know, and different impact factors, you get a whole load of energies that spread down there. And you also get error because your device can't accurately measure the energy very, very carefully if there's an error on the measurement. So in order to see this bit sticking out, you really need something very, very special. So here you've got this black line. Now it should go up there and sort of go across, and then it should go up there. But this line down, instead of being vertical, it's sort of diagonal. And you need to figure out that it's diagonal rather than vertical in order to figure out that the CNO neutrinos are there. And that's extremely difficult. You need a lot of neutrinos, and they don't have a lot of energy. And so you need a device that's got a very, very low threshold, an energy threshold, so it can detect very low energy neutrinos. Now, this is a machine in Italy in the same cavern as XENON 1 ton, which was called Borexino, and it's designed to look for these CNO neutrinos. For a long time, it couldn't, and people thought they'd given up. And the reason why it couldn't was because of everything that you build, whether it's XENON 1 ton detector or Super Kamiokande in Japan, or this detector, it's got little bits of normal stuff and dust on it. And you try and build stuff as pure as possible and test it before you install it, but it's going to have little bits of dust on it that are going to contain tiny contaminants of radiation, like uranium, which will then decay, and then you'll get like this decay chain. It'll lead to bismuth and polonium-210, tiny amounts. And these will lead to signals in the detector as well. So you need to try and get rid of them or understand how many there are. Because the 210 bismuth, which comes from this decay chain, is kind of roughly in the same place as the CNO neutrinos. And these 11 carbon neutrinos, they come from cosmic rays coming from the atmosphere. So you also need to make sure that it's deep underground. So that's why they put them inside mountains. Now, the problem they had was that they had sort of dust and radioactive dust that was on the surface of the vessel that was drifting into the vessel, drifting into the central volume where they were looking for events. and the radioactive decay was occurring, and they couldn't tell the difference between that radioactive decay and CNO neutrinos. So what they did was they covered the thing with insulators, a bit like you cover old immersion heaters to stop, to sort of shield the temperature differences and shield the temperature gradients so that you wouldn't get convection currents. And this crap that came from the walls would not convex into the central volume. And it worked. You can see over time, this is 2013 and this is 2020, the number of signals they were getting in the middle of the detector died down as they managed to reduce the thermal gradients, and they managed to detect CNO neutrinos, which is fantastic. That happened last autumn, but they couldn't tell how many CNO neutrinos there are. They couldn't get a good measurement of Z. They could just tell that they're there. Now, this is a major achievement just to see them in the first place, but we need to find out not just that they're there, but how many of them there are, so that we can find out what the internal structure of the sun is. And if we understand it well enough, we can find out if there's any new physics going on. Now, there's another experiment called SNO+, which people at King's are involved in, as well as Hyper-K, which is primarily looking for supernova explosions. Now, SNO+ was going to go looking for the CNO neutrinos, but they've decided to do something else. They've decided to look for neutrinoless double beta decay. I think it's because CNO neutrinos are so hard to take, just between me and you. Now, what's neutrinoless double beta decay? Well, here's beta decay of a nucleus. You get an electron antineutrino. Here's double beta decay, which sometimes happens. They both produce you get two beta decays happening at the same time. Neutrinoless double beta decay is no neutrinos come out. They sort of annihilate with each other. They are their own antiparticle. Now, that only happens if the neutrino is a Majorana fermion rather than a Dirac fermion. Now, I don't expect you to understand that, but it's a crucial property of neutrinos that people would like to understand. So while it's important to look for CNO neutrinos, it's equally important to look for neutrinoless double beta decay. And so what SNO+ has done is they've filled their detector with this stuff called tellurium, which does loads of double beta decays to see if they can spot neutrinoless double beta decay. But because that's in there decaying, they can't look for the CNO neutrinos. So later on, they might start to look for CNO neutrinos if they give up on, or they discover neutrinoless double beta decay, but it's still not clear they'd be able to discriminate between low and high metallicities. So maybe we need to use dark matter detectors to look for the CNO neutrinos. Now, we could look for these CNO neutrinos in two ways. We can see them bouncing off the electrons inside an atom and giving a recoil energy in that way, or we can see them bouncing off a nucleon in the middle. Now, it turns out that xenon also gives rise to huge amounts of neutrino double beta decay, right? So xenon detector is not a good place to look for CNO neutrinos because there's loads of double beta decay going on in there in the same energy range when you look at electron scattering. And it's not able to go for nuclear scattering. We don't think it's capable of going down far enough in order to be able to see in terms of energy threshold. So we need to think about other experiments. So there's two communities on the big dark matter detectors in the world at the moment, and they're both using liquid noble gases. So you've heard about the xenon people, but there's also a bunch of argon people. Now, they don't have the same background in the region where they're looking for CNO neutrinos, so they might actually be able to detect them, but only if they build a really, really huge one. And it also depends where they build it as well, because you get these cosmogenic backgrounds that come from cosmic rays. So you have to make sure that the cavern is deep, deep underground. And there's quite a lot of politics here because the cavern in Italy is not as deep underground as it's a lot nicer being in Italy, obviously, but it's not as deep underground as it is in either China. Well, I've never been to China, it might be lovely. Or South Dakota or Canada, where are the main places where you would look for this stuff. They're all a bit deeper and they've got lower backgrounds. The other thing that you could do is you could try and look for CNO neutrinos by scattering off nuclei instead of electrons. So you build a very, very sensitive dark matter detector with a very, very low threshold, and you hope that you can detect CNO neutrinos in this way. Now, this is how much exposure you need. Now, let me explain this. The horizontal axis is the energy threshold. You need to be sort of above this, sorry, below this line. What do you need to be? You need to be above this line, sorry, to detect CNO neutrinos, okay? So you need to have a certain exposure, which means you need a bigger experiment, which is running for longer, so that's in ton years. And you also need a low threshold energy so that you can get down to the very low energy neutrinos, because these neutrinos have got very low energies, and when they hit a nucleus, they don't give rise to a big recoil. So you need a very low energy threshold. For helium, you get a bigger kick because each helium nucleus is lighter, and the kinematics mean you get a bigger kick. So you don't need such a big energy threshold. But remember, I told you that the interactions with nuclei are coherent. So the matrix element scatters with all the nuclei in the nucleus. And so the probability goes like the number of nuclei in the nucleus squared. Okay. So if you go for a target which has got more nuclei in the nucleus, more protons and neutrons, then you don't need so much of it, but you do need a smaller energy threshold because it's more difficult to give them a kick that you can detect. And so people are building at the moment special new detectors that have got very, very low energy thresholds. For example, this one's called the NEWS-G experiment. So these can go down to very, very low thresholds, and you can put lots of different gases in them, which is very useful. And you can see if you get any recoils. Now, the problem is they're not very big, okay? And it's not a completely proven technology. People have been building xenon detectors now for a couple of decades, and the level of specialism people have got with detecting recoils from xenon is insane. But this, every time you develop a new technology, it takes a long time to fine tune it and get it really, really good. So these small detectors, they're not very big yet. So at the moment, they can't look for CNO neutrinos, but we're hoping that perhaps these kind of very, very low threshold technologies to look for dark matter can also see CNO neutrinos. And it's really important because the sun is right next door. It's our friend. It's the reason life exists on Earth. And we don't really understand it properly. And we use our knowledge of the sun and we extrapolate on it to work out all sorts of things about stars elsewhere in the universe. But if our understanding of the sun is not quite right, then we might be making some mistakes about other stuff in the universe. And so I think it's a real priority to try and detect these CNO neutrinos, and not only detect them, which has already been done, but find out how many there are very precisely so that we can find out how much carbon, nitrogen, oxygen there is in the sun, and then we can see what's going on deep inside the sun. And that will tell us all sorts of things, and it'll put constraints on all sorts of crazy new physics. So the ongoing search for dark matter continues. Dark matter detectors can also detect neutrinos, which is kind of a problem when you first think about it. But I think increasingly people are realizing that actually it's a good thing. So if you build a huge dark matter detector and a supernova goes off, of course, we've got hyper-K, which is going to detect loads of neutrinos from a supernova, but we're also going to get many hundreds of neutrinos from a dark matter detector, if it's big enough. And that will give us complementary information. And it'll be potentially via a different coupling, not just to electrons, but also to nuclei. So I'm very excited about these kind of things. And I think neutrino physics is, it's got a bright future, and it's very exciting what's going to happen in the next couple of decades. So thank you all very much for listening.
Thank you so much. That was wonderful. That was really, really interesting. And you did a great job, especially considering you weren't feeling that great.
Thanks. I'm feeling very lightheaded.
Still, you couldn't tell at all. It seemed like you were feeling completely fine.
Thank you very much.
Okay, so I'm going to share my screen again, just so that people can see the password. And then I'm going to hand over the word to our president, Nayera, and she will give everyone some more information about what's happening tonight and what's happening tomorrow. So Malcolm, thanks again. This was really, really, really interesting. And it was lovely that you're able to make it.
It's a pleasure. It's always a pleasure to come to Cumberland Lodge when I'm able to, but I'm really happy that you're doing something to replace it.
Oh, I just noticed, sorry, there's some questions in the Q&A. So
Yeah.
if you would like to, you could just.
Right. So the first one I can see is Gunter Singh. I don't know if it's Singh Gunter or Gunter Singh, apologies. I think it's Gunter Singh. Hey, Professor, please call me Malcolm. Why would dark matter particles be detected by ionizing electrons? Aren't they only gravitationally detectable? Well, that's the thing. They might not be just gravitationally detectable. They might have very, very weak probability of scattering with normal particles. And the reason why the weak interactions are so weak is because the boson, which mediates the weak interactions, the messenger particle that's responsible for those interactions, for those forces, it's very heavy. It's like 80 or 90 GeV, so it's 80 or 90 times the mass of the proton. So that means you have to get very, very, very close to a nucleus in order to interact with it via the weak interaction. Because these bosons are virtual bosons, so you need to borrow the energy from the vacuum, and using the uncertainty principle, because they've got such a big energy, they can only exist for a tiny fraction of a second, so they can't travel very far. So you need to get very, very close to a particle to interact with it via the weak interaction. So if I'm an electron and I see you, you look like a brick wall and I bounce off you. But if I'm a neutrino and I see you, you look like chicken wire. There's more holes than there are things to bump into, because I have to get very, very close to the wire to hit it. So it could be that dark matter does interact with normal matter, but only very, very weakly, because perhaps the messenger particle that couples dark matter to normal particles is very heavy. And there are some particle physics theories that people believe predict that that should be the case, but we haven't seen anything yet. How does securing funding and permission to build these experimental neutrino projects work? Is it easier than trying to upgrade or build a new particle accelerator, for example? If so, is it because of the size of the experiments? Yes. Yes. So it's the next, we want to build another particle accelerator in Geneva. The current LHC is 27 kilometers around. They want to build a particle accelerator that's more than 100 kilometers around, and they want to smash protons together in it. Some people do. I want them to. That costs billions. I can't remember if it's tens or it's a huge amount of money. Okay, you can discuss the cost of the LHC is approximately the cost of a research hospital to build, a big full-on research hospital. But then you've got to run it for years as well, which is more money. The cost of this next generation particle accelerator is really astronomical, and people would have to sort of have an existential, international, dedicated discussion about when they're going to do it. I think they will do it. I think we will always build a bigger detector. It's just that right now, geopolitically, it's very difficult to justify that amount of money. I mean, you could say that by bailing out the banks in the financial crisis 2008, 2009, they spent more money than it would take to upgrade the LHC, and that's true. But it's a bit different, isn't it? Because that's got a knock-on effect on the economy and it stops people from being unemployed. So it's a huge debate. Whereas building these dark matter detectors, they are small, they are very cheap. So far, they're very cheap. The next one, the next xenon detector, after the ones that are being built now, they're starting to get like really expensive. So they're starting to get like £1 billion maybe. Now, don't quote me on these figures, but we're talking about that kind of order of magnitude. So now it gets a bit harder to justify. And the other problem is that there isn't enough xenon, okay, on the planet. If you look at the global production of xenon, there isn't enough, right? And so people are buying xenon and having to store it because it's worth a lot, because it's very rare. So there's all sorts of interesting problems when it comes to that. I hope that answers your question. But up to date, the dark matter detectors are a lot cheaper. But if we carry on building them bigger and bigger, they're going to get more expensive, and we will have to justify them perhaps in different ways, like they're also able to probe neutrinos, for example. How would detectors be able to distinguish a dark matter signal versus other signals by neutrinos, cosmic rays, etc.? Someone says they want to answer this question. Shall I answer it? No, they've gone. Okay.
Oh, I think we can mark questions so that we can then dismiss them once you've answered them.
Oh, right. Okay. Right. So what you have to do is you have to fit all the, you get a big spectrum. So you get the neutrinos arriving from the sun. Some of them are from proton-proton cycles. Some of them are from CNO. Some of them are from polonium in your walls. Some of them are from bismuth. Some of them are from cosmic rays. So you need to understand your background really, really well. Really, really well. You have to spend a long time understanding your background, how radioactive everything is, how many gamma rays it's spitting out, seeing other things that come out of these radioactive chains to work out how much bismuth there is and what have you. And then if you understand your background well enough, you can then take into account the energy resolution of the detector and the errors, and you do what we call a chi-squared. So you try and fit everything with what you know about the background and the PP neutrinos, and then you try and fit it again with the CNO neutrinos in there. And if the fit is statistically better with the CNO neutrinos in there, then you can say, oh, well, I've detected CNO neutrinos. And how much statistically better it is by sigmas, that determines with what confidence you've discovered the CNO neutrinos. And if you discover them with very, very good confidence, not only can you tell they're there, but you can tell how many there are there. Could a detector the size of a planet or other astronomical object help to detect the dark matter particles? Well, I've done some work on this. I've looked at white dwarfs and neutron stars and very, very cool white dwarfs in globular clusters, because that's where the oldest ones are, and they get very, very cold. They heat up a bit if dark matter falls onto them, because the dark matter annihilates itself inside them and it heats them up. So if you look at the white dwarfs and you say, well, that one's really, really cold, it shouldn't have got that cold if there's dark matter falling onto it. So advice on getting into dark matter research: just work hard. I feel really sorry for this generation of undergraduates, because it's a lot more difficult to get onto PhD courses than it was when I was an undergraduate. I sort of did it with raw enthusiasm, but I was a little bit disorganized as an undergraduate. These days, you've got to be really top. And I feel sorry. I often wonder if I would have made it these days. So just try and get really good grades in your courses, and read around the subject, read popular science books, read New Scientist, read Physics World, and get books out of the library on popular science, complementary to your course. And then if you do get lucky enough to be in a PhD interview, you can tell them about all the popular science that you've read, and they're going to love it. And to tell you the truth, I would figure out how to code as well. Sorry. And also learn how to ride a unicycle while you're throwing plates in the air. That's a job. Why would dark matter particles annihilate the standard model particles? Well, they might not. It's a very good question. But sometimes we think that dark matter particles are their own antiparticles, in the same way that Majorana neutrinos might be their own antiparticles. And this class of particles we call WIMPs, and they're actually motivated by something called supersymmetry that we expected to turn up at the LHC, or quite a lot of people expected to turn up at the LHC. But unfortunately, it didn't turn up. And so people are now sort of scratching their heads. But if you say, but still we don't know why the Higgs boson has got the mass that it does have, because it's a scalar particle, and it's the first scalar particle we've ever seen. We don't understand the quantum corrections to its mass. Now, if there was supersymmetry existed, that would explain how it can have such a low mass. But without supersymmetry, when we write down the equations, it looks like the Higgs boson mass shouldn't be 125 times the mass of the proton, which is what it is. It should be much, much bigger. So we don't know why that is. We thought it could be due to supersymmetry, but in order for that to be true, then we should have seen the supersymmetric particles when we switched on the LHC, and we didn't. So people are now scratching their heads. But if in the theory of supersymmetry, you get dark matter particles that are their own antiparticles, and it works very well, and you end up with the right number of dark matter particles in the world today. So it's still a leading model, but it might not be true. They might not annihilate themselves. Could a detector the size of a planet or other astronomical object help detect the dark matter particles? I think I've kind of answered that. So I've looked at white dwarfs, but I've also looked at neutron stars, because if you dump enough dark matter particles onto a neutron star, you could in principle make it go into a gamma ray burst. You could trigger its collapse, because you get a core of dark matter building up in the middle, which screws up the equation of state, and it makes it unstable, and then you get gamma ray bursts. So people are looking at planets. In fact, there's a recent paper looking at planets in binary systems with the next generation of telescope. You know, the James, what's it called? The one they're sending into space, the infrared one. God, I've forgotten. The next big one. Anyway, they're trying to look for planets and see how hot they are, and they can put constraints on dark matter with that. If the new particle for interaction with dark matter is very massive weak boson, then what will happen with the Higgs mechanism and the 4-gauge bosons? How can it be integrated? Well, that's a very good question. It's beyond the scope of this talk, but I could you could have a look at supersymmetric models. You could have a look at 2 Higgs doublet models or 3 Higgs doublet models. They can contain dark matter particles. There's just a whole lot of theories where it works. Okay, I'm not going to answer that in more detail now, but thank you for the very good question. Can neutrinos be dark matter, or are they counted as normal matter? They can't be neutrinos. They can't be neutrinos because we know that neutrinos have got a very, very low mass. And we know that the neutrinos took place in the nuclear reactions which occurred like between 1 second and 1 minute after the Big Bang. So we know that we know what energy they've got. We know what kinetic energy they had then. And so we know what kinetic energy they've got now. And we also know that they've got a very low mass. So we know, just using the energy is the rest mass energy plus the kinetic energy, we know how fast they're going. And they're going too fast. So the dark matter, whatever it was not going too fast in the early universe. And so it was able to fall into tiny gravitational fluctuations and grow galaxies. But neutrinos would have been moving so quickly in the early universe that they would be going too fast to get caught by galaxies. They'd fly on one side and fly out the other without getting caught. And so they could never form galaxies. So it can't be neutrinos. It's a shame because neutrinos exist, and if they were dark matter, it would solve all of our problems, but they are not the dark matter. Anything interesting happening with the combination of neutrino physics and the buzzwords neural network? Yeah, well, everybody is using data science. I've written papers on trying to understand from gravitational lensing. If you've got a gravitational lensing images, can you use a convolutional neural network to work out how small the structures are that are responsible for the gravitational lensing? And that will tell you how quickly the dark matter is moving, because if it's moving too quickly, you can't get the small structures forming. So everybody's doing neural networks these days. Everybody and their dog is doing neural networks these days, which is another reason why you need to learn Python, everybody. What limits the sensitivity of dark matter detectors to CNO? Is the bismuth 210 background so stochastic that it requires too much data taking? Yes, but also, Joshua, you need a very, very low energy threshold. If you're going to detect it by scattering off nucleons, then, you know, for example, XENON they've done a brilliant job. The XENON people and the Lux Zeppelin people, both collaborations have done a brilliant job in getting a very, very low energy threshold, but it's not low enough to see CNO neutrinos by scattering off neutrons. Scattering off nucleons. So that's the big problem. And then you've got the additional problem that you then need loads of data for it to be statistically significant. So both of them is the answer. What kind of marks would I need to get a particle physics? Just try, I don't know. If you don't get a first, you're going to have to be able to talk the back leg off a donkey, all right? Right. Hi, Malcolm. Thank you for the interesting talk. You're very welcome. Thank you for listening. Are cosmic sterile neutrinos possible candidates for dark matter? Yes, there are. They are. So neutrinos are left-handed. All the neutrinos that couple to standard model particles have got left-handed helicity, which you probably won't understand until you do Chris's particle physics course, and I'm not going to teach you because Chris is an amazing lecturer, okay? There might be particles with right-handed helicity which don't couple to standard model particles, and they might have a different mass, and they could be dark matter particles. Now, they could, in principle, every so often, they could decay into a normal neutrino and emit a photon. It will take a very, very long time. So people are looking for those photons corresponding to their decay by observing the universe in X-rays. My understanding is that neutrinos can emit a weak boson in matter, leading to electron nuclear recoil. The weak boson travels between the neutrino and either the electron or the nuclear recoil to transport the energy momentum, which gives it a kick. Can a neutrino spontaneously emit a weak boson in a vacuum? If you had 2 neutrinos that were energetic enough and you smashed them together hard enough, you could probably produce a Z boson, which would then decay. But you can't have a neutrino decaying into a Z boson. Please don't call me sir, please call me Malcolm, but thank you for the respect, I do appreciate it, but I don't like professor or sir, I like Malcolm, as people who do my courses know. Do you think that the Higgs boson should be massless, since it's responsible for giving particles mass? That's not the problem. The Higgs boson should be really, really heavy when you take into account quantum corrections to its mass that work for other particles. We've got a way of figuring out quantum corrections to the electron mass in quantum field theory, and it's a bit different from what you expect. But when we do the same thing which works for electrons for the Higgs boson, then it predicts a really, really huge energy, and we don't understand why that doesn't happen. Hey, Professor, why would dark matter particles be detected by ionizing electrons? Aren't they only gravitationally? I've already answered that question. Is there an element which can survive continued exposure to the sun's surface? Am I doing these the wrong order? Yeah, the sun's surface is only 5,800 degrees. So if you want to break an element, you have to go to higher energies, right? The sun's surface is only high enough to destroy chemistry. It's not high enough to tear apart neutrons and protons. You have to go to typically 1 billion Kelvin to rip apart neutrons and protons. So the element, what is an element? It doesn't depend on how many electrons it's got. It depends on its neutrons and protons. So all elements can survive continued exposure to the sun's surface. Their electrons can't, they get stripped off them, but the elements themselves can. To get nuclear reactions, you have to go deep into the core. And the core itself is not actually hot enough for fusion to take place. So you need two particles that are right in the tail of the Maxwell-Boltzmann distribution to hit each other with much higher energy than the typical average energy for fusion to take place. So it's very rare. The motivation for dark matter interacting is commonly that it had to be made at some point. Is there a physical reason not to have such a bunch more fields that don't interact with our subset of stuff except from gravity? There are. You can write down all sorts of models with bells and whistles. You can have the dark matter on another brane, which is separated from us in space by some dimension which you can't see. There are so many models. If you can imagine it, Joshua, there is a model which is very close to your imagination. Because people have been working non-stop on this for decades. Do you think if we use a Dyson sphere to harness the sun's energy output and then accelerate particles to the speed of light? Yeah, maybe. I think you want to get to the center of mass being the Planck scale is what you want to do. So at the moment, the center of mass is like 13 TeV, so 13,000 times the mass of the proton. You want to get to 10 to the 19 times the mass of the proton. If you can go up to that in terms of collision energy, then you're good. Now, if it's a circular particle accelerator, then as it goes around the corner, it loses synchrotron energy because it's accelerating as it goes around the corner. So if it's going really, really high energy, it loses synchrotron energy really fast. So you need it to be huge so that it doesn't go around a sharp bend. And you need it to be like the radius of the orbit of Pluto, I believe. I don't know whether you need a Dyson sphere to make that work. And I've done it.
Great. I think that was it. I think you got through all the questions.
Thank you very much. Some very, very good questions in there, and it's a pleasure talking to you all. Thank you very much for coming today, and I hope I see you in real life before too long.
Yeah, it was lovely having you, and hopefully things will be back to normal soon, and hopefully you feel better as well.
Thanks. I'm feeling better already. Thank you very much.
Wonderful. Okay, great. I'm going to share my screen with all of you now and then hand over to Nayera. Let's see if I can get this to work. Here, can everyone see this? This should be fine. Okay, Nayera, I'm just going to promote you to co-host now.
Awesome, thanks. Yeah, so just want to say tomorrow at 1 p.m. we have a talk by Oleg, and that's Neutrinos Unifying Cosmology with Particle Physics. So that's again at 1 p.m. So do come along to that. And with these certificates, it's just, if you fill in the attendance form, you'll get the bronze one. And then if you fill in these mini quizzes that we'll send later, you can get this silver certificate instead. And we know that some people might not. If you fill in the mini quizzes, you'll automatically get the silver certificate, even if you haven't managed to fill in the attendance. So definitely do that. And also come along to our social today at 6 p.m, where we're going to be doing origami with Danush. And we're going to learn how to make a paper crane, and just, you can talk to us and get to know other people who have also come here. So we look forward to seeing you then. And that's everything. So yes, bye everyone.